Hello APC Mechanics student, today we'll solve the past paper of RQ Set 2 2022 exercise 1. Then let me start. A small sled slides across a rough horizontal table with an initial velocity v0. Then the table is rough, which means that we have friction. The coefficient of kinetic friction between the sled and the table is μk. A string connects the sled to a device on the ground. The device maintains a constant tension force. So the tension force is constant. This is important. In the string, by unwinding the string as the sled slides to the right, the total mass of the sled is m. The string is attached to the device at x is 0 and at a height of y. As shown in figure 1, the horizontal position of the sled is represented by x as shown in the figure 2. Express all algebraic answers in terms of m, mu, k, ft, x, and y, and physical constants as appropriate. Then now, whenever we determine an expression, we need to make sure that it's being expressed in terms of these. On the dot below that represents the sled, draw and label the forces, not the components, that are exerted on the sled at a short time after t is equal to 0, but before the sled has come to rest. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Then basically they're asking us to draw the FPD of the sled not at the initial position at x is equal to 0, however, when the sled is somewhere between x is 0 and x, so after x is 0. So basically the sled would be here. Now what are the forces that would act on the sled? We have the pull of gravity down. We have the normal push that is up. We have the tension in the string. Now after the sled moves, the tension would make a direction like that. So it's basically better to refer to this figure. Now we have the pull of gravity down. We have the normal push is up. So because the sled is moving to the right, then friction will be to the left. And if this is the angle theta with the vertical, then the string will also make with this vertical the angle theta. Now remember that it is not important to represent the angles on the FPD, but we're gonna do that because later on would help us in the projections. Then let me start as usual by doing the pull of gravity, which is down. We have the normal push to be up. Now I will represent the normal push to be greater than the pull of gravity because there is a pressing force, which is the tension force, helping the pull of gravity. Now the friction is to the left, opposite to the direction of motion. And in this case we're talking about kinetic friction. And here we have the tension along the string, which is connected to the sled, that makes an angle theta with the vertical. Now in part B, determine an expression for the angle theta that the string makes with the vertical when the sled has traveled a horizontal distance x. So basically we're talking about figure 2 when the sled has covered a horizontal distance x. We need to determine the expression of theta, then we can refer to this one. Now remember that if you compare figures 1 and figure 2, now that would be x and that would be y, and we're interested in determining theta, and this can be done by referring to any of the trigonometric functions, sine function, cosine function, or even the tangent function. Now here we can form a triangle if this is the point A and that's the point B and that's the point C. So AC would be the hypotenuse and would be expressed as radical y square plus x square. Then let me choose sine theta. Then sine theta in this case would be given by the opposite, which is basically x, divided by the hypotenuse, which is radical x square plus y square. And notice that we are interested in theta and not the sine function, but we can invert this function back again. Then let me write for part B by referring to the previous figure, we know that now sine theta would be given by x divided by radical x square plus y square. Then the theta function would be represented as the inverse function of the sine of the angle x over radical x square plus y square, and that would be our answer. Now it has been expressed in terms of x and y. Sine is just a function. Then indeed we have satisfied this condition in which the answers are expressed in terms of x and y. Now just a side remark, we should not add anything to the FPD. The FPD should be kept as it is. Now in part C, I derive an expression of the normal force Fn exerted on the sled by the table as a function of the position x. So basically, in order to utilize the normal push, we need to consider that the forces along the vertical are balance forces because there is no upward or downward motion. So I will say that the normal push would be balanced by the pull of gravity plus the tension force multiplied by cosine theta. Why cosine theta? Because we want the vertical component. If this is the angle theta, then cosine theta would give us the vertical component. And here I didn't implement any law, so let me say between brackets that I'm referring to the fact that these forces are balance forces. It is important to state any justification. Probably it's marked. Now we need to express our answer in terms of the things that they have mentioned on the first page. Now Fg would be replaced by mg. Tension is an allowed constant to be expressed as, now theta, cosine theta should be replaced by x and y. Now we need to refer again to the geometry of the figure. Now let me again construct the triangle that we have stated. This is A, this is B, and this is C. That would be AB is y, that would be the radical of x square plus y square, and that's x as stated here. Then cosine theta is the adjacent of the angle theta, which is y, divided by radical x square plus y square. Then let me replace this function here. So multiplied by y divided by radical x square plus y square. Then the normal push, let me again state my answer clearly. Then the normal push is given by mg plus ft multiplied by y divided by radical x square plus y square, and now let me close the bracket, and that would be the final answer for C idea 1. And now let's do the check that we have expressed in terms of the stated constants. Now we have m, g we can ignore because it's a fundamental constant, ft, y and x. Then let's check. Indeed we have m, ft, x and y. Then perfect. Now let's move to idea 2. Derive an expression for the magnitude of the net horizontal force F net exerted on the sled as a function of the position x. And here we should be very careful because we always should distinguish between the quantity, which is the vector quantity itself, and the magnitude of that quantity. If the quantity is said to be negative, we need to consider the absolute value of the quantity itself, which is adding a minus sign if it's negative and keeping it as it is if it's positive. Then we need to determine the net horizontal forces acting on the sled. Then let me say F net, which is the horizontal. Now what are the forces acting on the horizontal? Here notice that the positive direction is always stated like that. It's in the positive direction. So any force pointing toward the right is positive, any force pointing toward the left is negative. Now we're gonna refer to the FPD. Now what are the forces acting toward the left or along the horizontal? We have the friction and Ft multiplied by sine, because this would give you cosine and that would give you sine. Then we're gonna say that we have minus Ff corresponding for the friction, and minus Ft sine theta. Now for the friction, let me continue on the same line. Friction is given by mu k Fn independent of the state of motion minus Ft, and the sine function have been determined in the first part, and it's given by x divided by radical x square plus y square. Now comparing with the constants that they have stated in the question, mu k is fine, Ft is fine, x and y are fine. Now we need to replace Fn, but in idea 1 we have expressed Fn in terms of the given constants. Then let's replace Fn. That would be minus mu k multiplied by mg plus the tension force multiplied by y divided by radical x square plus y square. Now we close for double brackets, minus Ft multiplied by x divided by radical x square plus y square. Now notice that all of this net horizontal force is negative. Then the magnitude would be just multiplying that by a minus sign. But before I represent my final solution, it's better to arrange it in a representative form. Notice that this step is not mandatory, but we're gonna do that. Then here, let me say this is minus mu k mg, and I can factor out Ft, that would be minus Ft from here and here. Now we open a big bracket, we have mu k multiplied by this fraction plus, because the minus sign has been already factored, and now we can represent our solution as the magnitude of the net horizontal force. Then let me state that clearly. Then the magnitude of the net horizontal force is given by F naught, which is plus mu k mg. For the reason that I have stated previously, we should take the absolute value, plus Ft multiplied by mu k multiplied by the fraction, which is y divided by radical x square plus y square, the Pythagorean sum, plus x divided by radical x square plus y square, and now we close the bracket. Then basically this is our solution for C idea 2. Now in part D, we need to derive an expression for the work done by the string on the sled as the sled moves from x is equal to 0 to x is equal to L. Then the work done by a force is expressed as the integral of the force and the dot product between the force and the displacement. We follow the order that we're moving in from 0 to L. So that would state the boundaries of our integral. Now we need to utilize the force that is causing this work. It is done by the string, so this is the tension. Now referring to the FBD, Ft dot dx is the projection of the force along the displacement. The displacement is along the right, and that would be minus Ft. The projection of Ft along the horizontal, which is the displacement, that would add an additional sine theta function multiplied by dx. Then that would be minus the integral from 0 to L Ft, the sine theta function, multiplied by dx. Now Ft is a constant, can be dragged safely out of the integral, so that would be minus Ft, the integral from 0 to L. The sine theta function have been determined previously, and it's given by x divided by radical x square plus y square dx. And now we need to solve for this integral. As you can see that it consists of composite of functions. In the numerator we have x, which is linear. In the denominator we have the radical. Now you can ignore the integral and you can think about x square plus y square. Y is a constant because we're integrating over x, and in this case x square is quadratic. Then this integral can be utilized by the change of variable. Then let me say that u is x square plus y square. Then in this case du would be 2x multiplied by dx. Because here, notice carefully, we're deriving with respect to x, then u will be utilized as a constant. Then in order to transform this integral from being completely dependent on x to completely depends on u, now we need to find x dx, which is given by du divided by 2. Now we're ready to transform this integral. So minus ft, the integral from 1 over radical u. Why? Because our change of variable is set to be, this is u, then we still have the radical, multiplied by du over 2. Alright, and notice here something which is very crucial that I have done. I didn't place the boundaries for the integration. Why? Because these boundaries are defined for the variable x. I have done a change of variable, which means that we have reset the boundaries given by new boundaries. How can we determine the new boundaries? Simply by using the change of variable. This was supposed to be 0 and supposed to be L. Now we can determine the new boundaries by considering the change of variable. So in this case, u would be given by 0 square plus y square, which is basically y square. And this would be given by u equals to L square plus y square. So here, if we need to place the boundaries would be u square and L square plus y square. Okay, now a trick in order to avoid these steps is just to leave it as a free indefinite integral. Whenever we replace u again by x square plus y square, we will place the given boundaries. Now in this case, the half can be taken out, so this is minus ft divided by 2. The integral of u power minus half, because radical u is u power half, it will be taken up to be u minus half du. Remember that I won't place here any boundaries. That would be minus ft over 2. Now this can be utilized as a power function, so we add a power and we divide by the final power, which is u minus half plus 1 divided by minus half plus 1. Now still I won't place the boundaries because we didn't replace the expression of u. That would be minus ft divided by 2 multiplied by half u to the power of half, and yet the boundaries are free. Then half with 2 would cancel. That would be minus ft radical u from free boundaries. That would be minus ft. Now we're ready to replace u, so that would be the radical of x square plus y square. Now because we have replaced u back to be x, now we can set the boundaries from 0 to L. Now minus ft is a common factor. We open a bracket, and that would be the radical of, so we're replacing x by these, that would be L square plus y square minus the radical of 0 square plus y square. And that would give us minus the tension force multiplied by the radical of L square plus y square minus the radical of y square. Then the work done by the tension force, which is by itself negative, is given by minus ft multiplied by the difference of two radicals, and that would be our answer. Now in part E, they're telling us the sled comes to rest after traveling a horizontal distance x is equal to 2L. Now if you refer to the figures here, In figure 2, they have just represented the position of the sled at x is equal to L, or sorry, at any position x. Here, this is x is equal to L, so basically the sled will stop here for double the distance. As the system slides from x is equal to 0, x is equal to L, the energy dissipated by friction is E1. So from 0 to L, then this is not part of the answer, I will erase it later. The dissipated energy due to friction is given by E1. Now as the sled slides from x is equal to L to x is equal to 2L, so from L to 2L, the energy dissipated is given by E2. Is E1 greater than, less than, or equal to E2? Now, how do we know whether the dissipated energy is greater, less than, or equal? This depends on the friction. If friction is greater or less than, friction is a variable force. Friction depends on the normal push. Okay, so we need to check how the normal push changes. That would affect the change in the friction, and that would cause to either greater energy loss or less energy loss. Now, let's go back to the figure and try to check what's happening. So let me consider two different positions for the sled, position here and a position here, and check for each case how does the normal push changes. Now in this case, if you consider this case, so the tension here, so sorry, let me draw it more perfect. This is the tension, and that would be the tension here. So here, as you can notice, that the tension has a greater vertical component because it's aligned more toward the vertical. So let me consider even a better example. From 0 to L, we can consider it at this case. So at this case, the tension is completely aligned along the vertical. However, in this case, at the position between L and the double of L, the tension along the string is less aligned toward the vertical, which means the tension here, tension 1, is greater than the tension here, T2. So Ft1 is greater than Ft2, because for this position between 0 and L, the tension would be aligned more toward the vertical. As the sled moves from point A to point B, the tension would becomes more horizontal, which means it's losing its vertical component. As the tension decreases, the normal push decreases. Why? Because if you think about it, what causes the normal push to increase is whenever the tension becomes more aligned toward the horizontal. If the tension becomes more aligned toward the horizontal, the normal push would decrease until it reaches a value Fg. As the tension becomes more aligned toward the vertical, which means the normal push will increase. So let me repeat and say that in the first interval, the tension is aligned more toward the vertical, which causes the normal push to be greater, which means the friction will be greater. So now we're ready to write our conclusion. So the correct answer would be E1 is greater than E2, and let me say, since when the sled moves from x is 0 to x is L, the tension force is aligned more toward the vertical, which increases the normal push, and by that, why the friction will increase? Because remember that friction equals mu k Fn. As we increase the normal push, the friction will directly increase. By that, the friction increases, and whenever friction is greater, this means the energy dissipated is greater. Then the work done by friction is greater from x is 0 to x is L, and the energy dissipated E1 is greater than E2. Then that's it for me in this video, guys. See you soon in a new one.